Hi guys, so today we're gonna tackle what is intramolecular forces. By the way, my name is Mark Nidik in Algunas. So first, we're gonna define what is intermolecular forces. So what is intermolecular forces? Intermolecular forces are the forces of attraction or repulsion between molecules, atoms, or ions in a substance. These forces govern many physical properties of substances such as boiling point, melting point, viscosity, and solubility, and like chemical bonds such as covalent, ionic, or metallic bonds that holds atoms together within molecules. Intermolecular forces act between molecules. So there are three types of intermolecular forces. The first one is dipole-dipole interaction, hydrogen bonds, and London dispersion forces. So first, what is dipole-dipole interactions? It's a core between polar molecules where a permanent dipole exists through differences in electronegativity between atoms within the molecule. It is found in polar molecules, example HCl and SO2. Its strength is stronger than dispersion forces but weaker than the hydrogen bonding or ionic bonds. The example is the interaction between HCl molecules. The second one is hydrogen bonds. What is hydrogen bonds? It is a special type of dipole-dipole interaction that occurs when a hydrogen atom is bonded to highly electronegativity atoms such as nitrogen, oxygen, or fluorine and interacts with lone pairs of electrons on neighboring molecules. It's found in molecules with nitrogen and hydrogen, oxygen and hydrogen, or fluorine and hydrogen bonds. Each thread is strongest type of intermolecular force except ionic or covalent bonds. Example is water or H2O, ammonia or NH3, hydrogen fluoride or HF. The third one is dispersion forces or London dispersion forces. These are weak temporary forces that arise from temporary dipoles created when electron distribution within atoms or molecules fluctuate. Found in all molecules and atoms regardless of whatever they are polar or non-polar. It is the weakest type of intermolecular force, but the strength increases with larger and more polarizable molecules, more electrons or larger electron clouds. Example for this is noble gases such as argon and neon, and hydrocarbons such as methane and CH4. There are two other types of interaction, the ion-dipole interaction and the van der Waals forces. So, what is ion-dipole interactions? It occurs between an ion and polar molecule. These are significant in solutions of ionic compounds, such as Na+ interacting with water molecules. And the second one is what is van der Waals forces, a collective term for dispersion forces, dipole-dipole interactions, and dipole-induced dipole interactions. These are the importance of intermolecular forces. Number 1. Boiling and melting point. Substances with strong intermolecular forces, example hydrogen bonds, have higher boiling and melting points compared to those with weak forces such as dispersion forces. Number 2. Solubility. Like dissolves alike is based on intermolecular forces. Polar substances dissolve in polar solvents and nonpolar substances dissolve in nonpolar solvents. Number 3. Viscosity and surface tension. Stronger intermolecular forces increase viscosity and surface tension. Number 4. State of matter. The strength of intermolecular forces determines whether a substance exists as a solid, liquid, or gas under given conditions. Understanding this process helps explain the phenomena of chemistry, biology, material science, from the protein folding to the behavior of liquid and gases.
So, good day everyone. Today we're gonna talk about gases. In gases, we're gonna talk about measurement of gases, kinetic molecular theory of gases, gas laws, and gas mixtures. Measurement of gases. The mass of gas is measured in grams or kilograms. The volume of a gas is measured in liters or cubic meters. The density of a gas is mass or volume, such as grams per liter or kilograms per cubic meter. Manometer. A manometer is a device that measures the pressure of a gas or vapor. Some are made up of a U-shaped tube with a circulating column of liquid. As shown in the picture, we have two examples of a manometer. One is digital and one is not. The yellow one is a digital and the silver one is the non-digital manometer. Kinetic molecular theory of gases. Kinetic molecular theory states that gas particles are in constant motion and exhibit perfectly elastic collisions. Kinetic molecular theory can be used to explain both Charles and Boyle's laws. The average kinetic energy of a collection of gas particles is directly proportional to absolute temperature. Let's start with gas laws. Created in the early 17th century, the gas laws have been around to assist scientists in finding volumes, amount, pressures, and temperature when coming to matters of gas. The gas laws consist of three primary laws: Charles' laws, Boyle's laws, and lastly Avogadro's laws, all of which will later combine into the general gas equation and ideal gas law, which we're going to talk about later in the video. Let's start first with Boyle's law. Robert Boyle discovered the correlation between pressure P and volume V, assuming temperature T and amount of gas N remain constant. Here we have the equation P and 1 over V is to PV equals to X, where X is a constant depending on amount of gas at a given temperature. Here we have a given example, and feel free to pause the video so that you can observe the example and try to solve it for yourself. Here we have the given illustration and the solution. And take note, pressure is inversely proportional to volume in Boyle's law. Another form of the equation, assuming there are two sets of conditions and setting both constant to each other, that might help solve problem is P1 V1 is equals to X, which is the constant, equals P2 V2. Next we have Charles' law. In 1787, French physicist Jacques Charles discovered the correlation between temperature T and volume V, assuming pressure P and amount of gas N remained constant. V and T to V is equals to smaller case y capital T, where y is a constant depending on amount of gas and pressure. Volume is directly proportional to temperature. Unlike Boyle's law is pressure is inversely proportional to volume. Here in Charles' law, volume is directly proportional to temperature. Another form of the equation, assuming there are two sets of conditions and setting both constant to each other, that might help solve problem is V1 over T1 is equals to y, the constant, equals V2 over T2. Here we also have another example of Charles' law. You can feel free to pause the video and examine the example, and you can try to solve it for yourselves. Lastly, we have Avogadro's law. In 1811, Amedeo Avogadro fixed Gay-Lussac's issue in finding the correlation between the amount of gas N and volume V, assuming temperature T and pressure P remain constant. V and N is to V equals Zn, where Z is a constant depending on pressure and temperature. Here in Avogadro's law, volume is directly proportional to the amount of gas, while in the Charles' law, volume is directly proportional to temperature. Another form of the equation, assuming there are two sets of conditions setting both constant to each other, that might help solve problem is P1 over N1 is equals to Z is equals to P2 over N2, where Z is a constant. Here we have an example. Feel free to pause the video and try to solve it for yourself. And next we have the solution for the given example. Next is the ideal gas laws. The ideal gas law is a combination of the three simple gas laws. By setting all three laws directly or inversely proportional to volume, you get Vn, V, and Nt over P. Next, replacing the directly proportional to sign with a constant R, you get V is equals to R, smaller case n, capital T over P. And finally get the equation PV is equals to N RT, where P is the absolute pressure of ideal gases, V is the volume of ideal gases, N is the amount of gases, T is the absolute temperature, R is the gas content. Here R is called the gas constant. The value of R is determined by experimental results, and its numerical value changes with units. And lastly, we have the general gas equation. In an ideal gas situation, PV over nRT is equals to 1, PV nRT equals to 1, assuming all gases are ideal or perfect. In case where PV over nRT is not equal to 1, or if there are multiple sets of conditions, just like pressure, volume, number of gas, and temperature, use the general gas equation, assuming two sets of condition, initial case to final case, so PI over PI VI is equals to NI R TI. PF VF is equals to NF R TF. Setting both sides to R, which is a constant, with the same value in each case, one gets R is equals to PI VI over NI TI. R is equals to PF VF over NF TF. If one substitutes one R for the other, one will get the final equation and the general gas equation, PI VI over NITI is equals to PF VF over NF TF. Next, we have the van der Waals equation for real gases. It's pronounced Waals, the W is pronounced V, so that's van der Waals equation. Dutch physicist Johannes van der Waals developed an equation for describing the deviation of real gases from the ideal gas. There are two correction terms added into the ideal gas equation. There are 1 plus AN2 over V2 and 1 over quantity V minus NB. Since the attractive forces between molecules do exist in real gases, the pressure of real gases is actually lower than of the ideal gas equation. This condition is considered in the van der Waals equation. Therefore, the correction term is 1 plus AN over 2 V2. Corrects the pressure of real gas for the effect of attractive forces between gas molecules. Similarly, because gas molecules have volume, the volume of real gas is much larger than of the ideal gas. The correction term 1 minus NB is used for correcting the volume filled by gas molecules. Lastly, gas mixtures. A mixture of two or more gases of fixed chemical composition is called a non-reacting gas mixture. Consider K, the gases in a rigid container as shown here. The properties of the mixture may be based on the mass of each component, called gravimetric analysis, or on the moles of each component, called molar analysis. Many thermodynamic applications involves mixtures of ideal gases, that is, each of gases in the mixture individually behaves as an ideal gas. In this section, we assume that the gases in the mixture do not react with one another to any significant degree. We restrict ourselves to a study of any ideal gas mixtures. An ideal gas is one in which the equation of state is given by. And that's all for the video today. I hope you learned many lessons, and see you around, and God bless and have a good day. Thank you.